So we started discussion about the scalar transport form. Okay, so in the what we did till now, we try to generate the passive scalar transport form, then we add the scalar equation inside the ICO form as well as simple form as well. Okay, so now let's also add this scalar equation into Piezo or pimple form. Okay, either of these things. So let's go to the incompressible area. So we have two options, either Piezo or pimple. So I'm going with the Piezo form, and I giving you the assignment to incorporate this scalar transport equation inside the pimple form. So let's begin with the Piezo form. Okay, so let's kept here as a Piezo form, and what we want to add this scalar transport equation inside the Piezo form. So let's first rename based on our requirement. So let's say Piezo scalar transport form, that is our name of the solver. Okay, now immediately rename the .c file, go to the make folder, also rename the file as well. Don't forget to type user here. Okay, so if you don't type user here, by default it will go to the our release version of the folder, but we don't want that way. So it is better to transfer our new compiled application inside our own area. Okay, so that's why we are typing the user there. Now let's first compile this and make sure that our template is ready to go. So OF 3.0x. Before you go for compilation, type wclean.all, then let's say wmac. So we are constructing the application, so no need to type wmac libaso. If you want to construct the library and that we want to link dynamically, then only it goes libaso, otherwise wmac only. So we are set with this. Now what we want scalar transport equation here. Okay, so for that let's construct the new equation, let's say T equation, that is what we needed. Okay, and open the this and also T equation. So remove all this entry. So we have a T equations. So T equation we supposed to copy from the area of scalar transport form. So go to the basic scalar transport, open this file, and here is this value, Control C, kept it inside here. Okay, here we are working with the simple loop, but we are working with the Piezo, so we supposed to use the Piezo loop as compared to the simple loop. Okay, Piezo non orthogonal character, that is what we needed, so that is we are adapting from here. Okay, fine. Now we are set, sorry I changed it wrong locations, so let's close this. We supposed to change here as a Piezo form. So we are set with T equation, but when we add the T equation we require two variables to be added. So one is T, another is dt. So let's open the create field file. Okay, so let's add up this T equation reading a T, okay, inside the create field file. So let's say read the T. Okay, along with that we also supposed to read the this transfer property is the dt. So let's check inside the create field file, do we have a that transport property reading entry? We don't have, so let's quickly add up this. So here we are reading the transport property. Okay, and dt is the diffusivity that we're going to use inside the this transport equations. So we are set with equation, we add the transport property, but we have to incorporate this equation. Okay, so we supposed to incorporate after the all the correction is over and before the writing. So let's say type this include and our equation name, t equation.h file, so that is we incorporated here. Okay, so with the help of that we are set with the solver development, and it's very easy. We need not to do so many things to incorporate this one very simple equation. So we incorporate t equation.h file here. We constructed two new variables. One is the dt, okay, that is required, and another is the t, that is the volume scalar field. Okay, so if the new variable is scalar, then we say volume scalar field. If it is vector, then we say volume vector field. Okay, but what we develop is the scalar one. Okay, and we want it's supposed to be read as well as auto write, so that's why it says must read and auto write, and it's the part of the mesh because it's belong to the volume scalar field. Same way the dt is a dimensional scalar. Okay, and we try to read the dt from the transport property area, so that's why we have that entry here. So we are set for compilation, so let's check everything fine. So our Piezo scalar transport form is ready to go. So I suggest please try to run the Piezo scalar transport form with the help of our test case. This is whatever we have in this flow over circular cylinder. So add up the test case and try to run this Piezo scalar transport form with the same setting, and make sure you are also able to get the vertex shading out of it. So that is the idea. Okay, so that is very simple way to incorporate the scalar transport equation inside the Piezo form. So let's go to the release area, okay, and application solver and the incompressible. So I suggest in the similar line, please incorporate the scalar transport form inside the pimple form as well. Okay, so when you add that entry in the pimple form, you have a scalar transport embedded all the solver like icoform, piezo, pimple and simple. All the form is available with this very nice entry. Okay, so that is how one can quickly adapt the solver development for simple class of the scalar equation. So if you go to the base, you have a Laplacian as well as potential form and the scalar transport. So whatever the very simplified equation you required, you can adapt either of the way and try to adapt that methodology and incorporate wherever needed very quickly. Okay, so that is the one thing. Now let's do few more modification in the solver development point of view. So if you look at the incompressible form, okay, and if you look at the ICO form, so let's look at the description of ICO form, okay, what it suggests us. So let's look at ICO form. It says transient solver for incompressible laminar flow of a Newtonian fluid. Okay, so it's going to work for incompressible flow and laminar flow only and Newtonian fluid. Now let's look at the Piezo form. Okay, so Piezo form, if you check, it says it's transient solver for incompressible flow. So same thing, transient solver for incompressible flow, same entry, but it has a turbulence modeling, okay, like laminar runs and LES. So it has an embedded turbulence modeling enabled. So what change we can make inside our ICO form so that you can also activate the turbulence modeling inside the ICO form. So how to modify this ICO form so that it is allow you to look at the turbulence modeling inside the ICO form. So let's understand few of these changes so that so whenever in any of the solver we want to incorporate the turbulence, we know that this few entries we have to modify inside the solver so that we can have a modified version of the solver, and along with that we have a turbulence model enabled. Okay, so how to proceed? Let's first copy the ICO form, okay, from that area. So I'm copying this ICO form and keeping inside our area, paste it. I am writing it as a my ICOFOAM. Okay, my ICOFOAM with turbulence, with turb form. Okay, so in this we have to incorporate the turbulence modeling. So at least we come to know how to add the turbulence modeling, so that sometime we want to tune certain solver with the turbulence modeling and all this thing, we come to know that what addition part is required inside the solver. Okay, so let's start with same name. So we change the name. Okay, so we are doing simple modification, so it gives us the idea how to work with the OpenFOAM environment as far as the solver development is concerned. Okay, so we name the C file, we change as a user application bin, and our executable file also we change with respect to that. Now let's, before we go towards further development, let's create few equations that normally we are doing. Okay, so we say that we require the U equation file, along with that we require the P equation file. Okay, so we are developing few equation files, so let me first open this as well as also open this, both the files. Okay, so let me delete and clean the area. Okay, so in the U equation file we know that what supposed to copy, so this all entries goes inside the U equation file. So let's do that. So this U equation file is ready to go, and along with that let's write down U equation file here. Okay, then this is the P equation, so everything inside of this piezo, it goes inside the P equation file. So let's copy that, save. Okay, so P equation, so let me delete this area, and we say that this is nothing but the P equation area. Change the name as a P equation. So we are set with the solver, whatever we have at present, but we yet to modify based on our requirement. Okay, so solver is up to date, no change required. Okay, so we are set. Now what change we supposed to do inside this solver, so that we can allow the turbulence modeling inside of our this particular solver? For that, how to proceed? So we supposed to identify the most relevant turbulence modeling type of the solver that is very close to our development. So let's say look at the Piezo form. Okay, so that is more close to the what we are hoping. So inside the Piezo form, what different things we have to add? So we have to look at, now just compare header file first. Okay, so if you look at the header file for without turbulence modeling, we have fv cfd.h and piezo control only. Okay, but when we want to incorporate this turbulence model, we supposed to activate this both the header file here. Okay, so I'm adding this to header file, single phase transport model and turbulence model.h file. Okay, so and this is belong to the FV option. If you want to incorporate the FV option, then only you activate this. What this FV option going to do? It try to enable this runtime selectable MRF and finite volume options. Okay, so you can add the explicitly some source term like a porosity and all this thing with this option. So right now, if we are not interested, don't activate this area. Then so we are set with this header file. What different include? So it is same what we needed here. Okay, then MRF we not required, FV option we don't required, continuity only we required. So that is the two files already there. Okay, then any further change here? No further change except this two line required. So later on we add. First let make sure that whatever the header file we incorporated is added properly or not. Okay, so maybe we able to face certain errors, so we supposed to be ready to for that. If we able to Okay, sorry, I didn't change the location. Okay, so let me go to the our area. Okay, now let's, okay, so look, single phase transport model.h file, no file or directory. So it's saying that this file or directory is not available. So that means our solver is not able to see this file .h file. So where this .h file is available, okay, so that location is supposed to be incorporated, but where? So whatever the new library we want to add inside the solver, so this is what this libraries is available inside it, inside the src folder. So we have to direct our solver towards that area and try to fetch that library from that area. So how to do that? For that, go to the make, and here is the option. So open the option area. Look, in the option area we have only these two libraries. Okay, in the similar line, if you look at the option area for Piezo, we will see couple of few things. So here we have this single phase transport model. So we supposed to incorporate this two line. So if we incorporate this two line, what going to happen? Just check. If we add this two line single transport, okay, incompressible turbulence and incompressible transport model we required. Okay, so this model also we have to incorporate here. Okay, this order doesn't affect, so don't worry if one is above another is below, or you can cap this above and below, not an issue. Okay, so with this let's check anything. So we also, along with that, now that error is gone. Look, single transport model.h, no file and directory, that error is gone. Now on the line number of 34 of our main source code, so just go to that area, line number 34. So this turbulent transport model.h file is missing. Why it is missing? Because the entry inside the option is not available. Okay, so first we incorporate the transport model, that error is vanished. Now we incorporating about the turbulent modeling. So we supposed to add this two line. Okay, if we add this two line, okay, we are set with the turbulence model. Along with that, we supposed to also incorporate this libraries. Okay, so we are incorporating this library as well. Okay, so we have a turbulence model, its library, and the scalar transport library. Okay, so let's check with this. So this is called resolution of dependency. So whenever you come across certain class of the errors, okay, so and we don't know where exactly we can look at, so that we able to resolve this error. Okay, so let me revert back this change. Okay, let's say we don't know this incorporation of this two line, so how to resolve it? Okay, so let's understand that aspect as well. So if I do that, we will find this error. So this error suggests that the no such a file or directory available. It means that whatever the path we set for including certain libraries and certain source code is not available in the options files. Okay, now how to check that? How to check what option entry we supposed to add, so that we able to resolve this error? For that you have to follow few things. So let's go to our install area. Let's say right now I know that from the Piezo, if I add up this two entry, it's fine, but sometime we developing few different class of solver and we come across some different library missing, or that file is not the part of it, and that type of error. So how to resolve? For that, best part is to go towards our install area. Okay, so let me go towards our install area. So let's say here is our install area. So first always check inside the application solvers. Okay, any place anybody is using that file or not. Okay, so very quickly one has to check that. Okay, so what I mean, go to that folder. Okay, whatever the error we are getting the turbulent transport model dot file h file that is needed for our calculation is missing. So first grab this file and check where that file is available. Okay, so this file inside the application solver, if you see so many places that file is incorporated. Okay, so if you go to the incompressible, if you are working with incompressible, go with the incompressible. Okay, heat transfer also, it has that files. So if you open any of this area, okay, and in that particular area, go there and try to open the option file of any of this. So if you go to the, let's say, simple area in the solver, let's say incompressible simple form, and look at the make and option area, you must have that entry. So look, that entry is available here. Okay, so simply copy this to entry from this area to the your area. Okay, fine. Along with that, this turbulence model, this to entry also required. Okay, so this is include file, this is library. What is the difference? I will tell you very quickly. What is this to difference? Why this to entry required? So look, this is the include folder. So what it suggests, this whatever the needed file, it is available inside this single phase area. So what is this? lib src transport model, incompressible single phase transport model. So let me guide you that area. So src folder. Okay, so you go to the here, what it suggests, lib src, that means you go to the src folder. Inside the src folder you have a transport model folder. So search for transport model folder. Inside the transport model folder you have incompressible. So incompressible, inside that you have a single phase transport. Inside of it you will find this file. Look, single phase transport model.h file is available here, and that file we are incorporating here, single phase transport model.h file. In same line we want to incorporate turbulent transport model.h file. Okay, so how to find that file? So go to the again this area option. So we have a turbulence model. Okay, and in turbulence model include or turbulence model, inside that you have a incompressible and include. Okay, so both the either of this place you will able to see that file. So let's go to the src. You have turbulence model. Inside turbulence model you have again turbulence model. Okay, and you have a ln include. So here you must have that file. So which file we are looking at? We want to incorporate the turbulence transport model.h file. So just check turbulence transport, turbulence model.h file we have. Okay, so but we require turbulence transport model.h file. So let's go to the other area. Okay, in case of this it is supposed to be in here. Okay, turbulence transport model.h file. So it is available inside the incompressible include area. Okay, so incompressible include area, so that is what we added here, and it facilitated that part. Okay, now this is the all the header files that we are including. Okay, so if you want to resolve any of the header files that is needed, we have to incorporate that in ln include path, or wherever that file is available up to that path here. Okay, and what about these two files? This is the after compilation it try to generate the lib incompressible transport model library file or lib incompressible turbulence model library file. That files we want to incorporate by exe_lib equal to. So when we incorporate anything here, from where it going to fetch inside our solver, it going to look at in this area. So it goes in the our installed version, go to the platform 64, in the it is belong to the lib. So lib and all the libraries what we are writing here, L incompressible transport model, it's supposed to be there. L incompressible, just check, L lib incompressible. Okay, lib incompressible transport model. Yeah, here lib this is compressible. Same way you must have some incompressible transport model library also be there, compressible transport model. Okay, lib incompressible transport model dot so file. Okay, so when you type this, it try to look at that part from the transport and turbulence model, both the things. Okay, lib incompressible transport and turbulence model. So both the files now it align with our developed solver. Okay, so that is why this library resolution is very, very important when we are incorporating certain files. Okay, so till it's saying that turbulent transport model .h file, no such a file or directory, because we didn't save this file, that's why. Okay, so with this we able to resolve the dependency, that is what coming from the new incorporation of turbulence model. So we are set with this. So I hope you understand. So whatever the libraries we have to include, we have to assign the path inside the option folder. So we are incorporating two libraries, single phase and the turbulent transport. So for that we have this two line for turbulence models and two line for transport, and whatever the library we have this fv cfd.h, for that this is the include file name. Okay, so that is what normally we required. So that is all incorporated as a options. Now what other change is required inside the solver, so we able to take care of generic turbulence modeling. So we incorporated the transport models. Okay, so we are set with this. Along with that, if you now compare the files, okay, so let me first switch off this. So we are set here. We supposed to also incorporate laminar transport model correction and turbulence correction, this two entry after the our piezo loop is over. So after the piezo loop is over, we supposed to have this two entry over here. Okay, so this two entry is needed before the write. Along with that, what different change? So this turbulence corrector, what it going to do? It try to solve depending on our selected turbulence model. It try to solve the turbulence model with this entry. Okay, so it direct the solver to the particular library. If we are working with k epsilon model, it going to use the k epsilon model, k omega. Based on our selection, it try to look at the turbulence model and try to solve. Okay, along with that, what different few more changes required. So if we are working with that, okay, so turbulence transport model we incorporated, what different other change? So let's compare the U file. Okay, so if you look at the U file for our case and the piezo, we will see certain difference here. So in the U file, so in our case we are directly using the only laminar kinetic viscosity, but when we work with the turbulent flow, we have a two part of this viscosity. One is coming from laminar side, another coming from the turbulent side. So for that purpose, we have to incorporate some different line like this way. Okay, so we are adding turbulent dev re effective. Okay, what it going to do? It try to take into account the effective viscosity and try to utilize the Laplacian term, or try to look at the Laplacian term in the similar spirit. Okay, so that is the idea. So this line I am commenting. Okay, so in case of this, we require this line. What else? This is because of MRI we don't require. This is FV option we don't require. Then under relax. Okay, so sorry, yeah. Then what else we have? We say under relax if you want to do that. Okay, then you can say, let's say under relax. So if you say under relax, it try to under relax the our solver as well. Okay, so under relaxation we kept, okay, U equation, and then we say piezo momentum correct predictor. If yes, then it try to solve for equation. If no, then it only generate the matrix, and that matrix going to use inside the P solver. That is what it going to happen. This is not required, it is belong to FV option. So we are set with the our momentum predictor. So that entry we added. So now let's check we didn't generate any additional error here. Okay, so we say laminar transport was not declared in the scope. So we supposed to declare certain laminar transport type of the things inside our solver. So where to declare that? So it normally all different variables and all this declaration is normally goes inside the this create field.h file. Okay, so create field.h file, let compare for our case and the piezo case. So if you look at the create field.h file, okay, sorry, here, so we have a what we have here in the create field. Okay, so we say p u equation create field, okay, and then we say reference values, okay, based on the piezo, okay, set flux required for p. Okay, so this all entry we are keeping. Okay, so all this fine, create field fine, u is fine. Okay, but we are reading this transport property, but here we are not reading the transport property. So let me comment this area, okay, or delete that area. Okay, so we don't require this entry. If you read it, no worry, it's not going to harm you. Okay, so don't worry about that part. So don't delete that. But along with that, what we have a single transport model and incorporation of this laminar turbulence model. So let's do it at the end. So this 2 entry required, it will, with the help of this, what it going to do, it try to read the new whatever you are reading here. It's so multiple time we are going to read the new based on, with this entry it allow you to read the new as well. Okay, so don't worry about. And here we are creating the pointer for the turbulence, and this pointer going to use here for this place. Okay, and with the help of that we are set with this one error, laminar transport, whatever it is giving us the error, that is be able to resolve this laminar transport as an error. Okay, so let's look at it. So with the help of that, I think we are set with our transport equations. Okay, so we are set with the transport equation. We incorporate this transport equation very neatly inside of this our solver. Okay, so now we are set with the new solver that we developed by our own. It will allow us to take into account any type of generic turbulence modeling. So I suggest use this and adapt any of the standard tutorial from the release version. I say standard tutorial, go to the tutorial area, okay, and look at the incompressible and piezo based solver we develop. So adapt any, let's say, RANS based tutorial, try to solve it with our solver and also solve with the standard piezo form and try to compare both the result. And it's not supposed to change even by 1% also. Okay, so our solver and the standard piezo solver both supposed to give you the same result. Okay, and it if not give the same result, that means still there is some error, but I am pretty sure there will not be any error in both of them. But last file we supposed to compare is the p equation file, so let me compare that file as well. Okay, so p equation file, if you see, okay, so here we have nothing related to turbulence correction. Okay, so that is this FV option we are not using, so no worry. Okay, if you want to incorporate the FV option, then this entry here required. Otherwise we don't require any modification with respect to turbulence model selection or anything inside the p file, so we need not to change here anything. So with this we are set with this. Now let's incorporate few more entries in this particular developed solver. So what we developed here is simple solver. Okay, so now let's incorporate the temperature equation in it. So how to do that, let's understand that. So solver, let's say heat transfer. Inside the heat transfer, let's say bound simple form, and here we have energy equations. Okay, so energy equation we have, so for that we require the thermo, but I don't want to go toward the thermo route. Okay, so thermo, that means it's based on the sort of compressible environment, so I don't want that class of solver. So I want T equation based solver. So this is pretty good. So let's try to incorporate this T equations from here inside our developed solver. So we have a energy equation, entire energy equation. If you want to incorporate, then how to proceed, let's understand that as well. So let me close this, but I want to develop a entirely new solver for that. Okay, so what I do, I add up the, let's say, pimple form. Inside the pimple form, let's say incorporate this energy equation. So we have a few more solver development aspects. So let's go to the first application area, solver incompressible, let's say pimple form. Okay, so let me copy the pimple form from this area, and in this we try to incorporate that energy equation inside of it. Okay, so let's have a pimple form. Okay, so pimple form, rename it pimple, okay, energy, pimple energy form, that is the name I gave it. You are free to choose any name, so there is no any restriction about the name selection. Okay, so we are set with this. Again, rename it pimple energy form. Immediately in the make folder also change the same pimple energy form. Okay, don't forget to say user here. Okay, so pimple energy form we are set. Now first recompile, so we are sure that what the change we did is correct or not. So before that, let's say wkey all wmake. Okay, so we are set with this let's say pimple energy form. Okay, here we going to incorporate the energy equation, and that energy equation we going to add up from the heat transfer area. Okay, so that is the idea. So pimple energy form, and in case of this, go to the heat transfer. Here we have a bouncy pimple form, so from that area I want to add up this one file. Okay, so and I want to simply copy this file, and then we try to attach this file inside our solver. That is the idea. Okay, so our basic platform is ready to go. Now let's look at first this entry, along with that this file. Okay, now this file we have to do certain modification, so later on we do, but first understand here as well. So Bossinus pimple form we have. Okay, so and where we are plugging this after the u equation, we are plugging this one file. So same way we supposed to plug inside our pimple energy form. After the energy equation we plug this t equation file. So location we fixed. Okay, now let's first straight away compile and we generate few errors. Okay, so we understand what is the lacking and all this thing. So it give us certain errors. It's saying that Hrvoje and all this thing is missing, but if you look at the t file, so make sure we don't require this Hrvoje. It is belong to the dynamic pressure. We are working with our standard pressure, so don't worry about that part. So delete that entry. Okay, so Hrvoje error is because of that, so we clean with that error. Now few more errors is available. We said that this correction of t, so t is undefined variable first of all, so we want to set the t inside the appropriate location. So where to set? Go to the create field. So we didn't create a new field, so go to the create field from this area, and Bossinus pimple form also go to the create field area and add up this read t entry from Bossinus towards our area. Okay, so we read the t. Then what else we needed? If you look at the t equation, we have a something like alpha t. Okay, and then correction of alpha t, we require the nu t and pr as well, prt. So okay, read transport property dot h file is additional file we have inside the heat transfer area. Okay, so read transport property is the one of the file it going to read the property. Okay, no worry, so let it be there. Okay, in the similar line, in the create field of our area we don't have that entry. Later on we fix based on our requirement. Okay, along with this, what else we needed, just check. In the create field .h file we have a t, this, then u. Okay, Hrvoje. Along with that we have a kinetic turbulence thermal conductivity. Okay, so that is alpha t we required. So let's incorporate this entry inside our create field.h file. So where we are incorporating after our turbulence initialization. So after the this we are adding that entry. So alpha t we added. Okay, so this Hrvoje not required. Then we have a gravitational extension not required. Okay, then P not required. We reset the cell value for reference pressure, it's perfectly all right. Flux for pressure, it's fine. Okay, only thing is remaining is read this transport property.h file. So for that we have to check where exactly this file is located and what they are reading inside of this particular file, or straight away we can adapt this read transport property.h file inside our area, but where we are keeping after create field.h file. Okay, so after create field.h file we are saying that let's read the transport property.h file. Okay, so after that we have a this all the reference values, then this, and we are reading this. If you want you can keep this file all the reading beforehand as well, so don't worry about that part. Okay, alpha t. So let's see now what is missing. Okay, so we are almost there, but we not able to set the read transport property.h file. So how to fix that read transport property.h file? So it is somewhere other locations. Okay, so for that let's look at the options first. Option, any place we have transport property. Okay, it is from here, Bossinus simple form. Okay, so if you go to the Bossinus simple form, it has that file. Okay, so read transport property, if you look at this file, it try to read all these entries, so that is what we needed. So we add up that file from here. Okay, and paste this in our area and try to modify based on our requirements. So beta is the thermal expansion coefficient, that is not needed. Why not needed? Because we are not working with Bossinus approximation. T reference value is also not needed because we are not working with the Bossinus approximation. We required PR and PRT and the single phase laminar transport model. Okay, so that thing we required. Okay, so single phase laminar transport we are adapting here, so it is 2 times, so either we remove from here, that is better. Okay, so here we require this only 2 things to read from the laminar transport property. Okay, so laminar transport property, after that only it's supposed to be created. That means these files, okay, it's supposed to be after this line only, otherwise it's going to fail. Why I say it is going to fail? Because this laminar transport property, that file, okay, it's supposed to be after that only, otherwise it's going to fail. So what else? Somewhere we have a, in the T equation, few more entry we have that we supposed to change. So T equations, fine. So this is our alpha T, this is our alpha. Okay, so and this is effective alpha that is needed. This about the radiation, if we are not interested in radiation model, and the FV options, let it FV option be there, but radiation we are not, let's say, interested. So remove that radiation part, also remove this radiation part. Okay, and we are set with this FV option, fine. Okay, so let's see. So pimple energy equation is ready to go. Now let's run this case. Okay, so we have idea at the running case also what modification is required. So here go to our test case area, and okay, so let's generate the new test case for this as well. Here 003, let's say, equations. Inside of it I am adapting whatever we have in the previous case. Okay, and we supposed to modify based on our requirement. Okay, so here first of all this block mesh, let it be, but this control and FV options we have to change because it is belong to the Piezo algo. Now we work with the pimple algo, so let's first change that area. So go to the install tutorial incompressible. Okay, and just look at the pimple base, let's say any of the things if you adapt. Okay, and select this entry. So we are set with that. If you now look at the control dict file, it is based on this, but changes to energy. Okay, and latest time, find delta t, whatever we needed. Let's say delta t is supposed to be 0.5. okay, and writing interval. Okay, so we add up the same writing interval. It is adjustable time, so every 1 second it's supposed to write. This is 1, end time equal to, let's say, 100. okay, so adjustable runtime current number we fixed equal to, let's say, 1. Depending on that, it try to adjust the delta t. Okay, so let's start with the delta t, some lower value. Okay, and it going to adjust accordingly. So pimple energy is fine. Now let me open the same location for calculation point of view, and we have to modify certain things over there. Let's say OF 3.0. okay, let's see. So alpha cannot find alpha t that is needed for our requirement. So from where to find the alpha t? Go to the energy equation, heat transfer area, heat transfer, Burns pimple form, hot room. Here we have a alpha t, so copy this file into our area, paste. Okay, so open this and this, both the files. Okay, so alpha t and t, so this is the entry. So inside the alpha t we have to change certain values. So in the floor, that is mean it is the wall, so wherever we have wall we have to adapt this value over here. Okay, floor, ceiling, otherwise alpha t, it's, if it is an inlet or outlet, let me keep the same value. So we are set with that. Okay, now what else we needed? Just check. PR is undefined in the transport property area. Okay, so go here, transport property. If you open this, we have that entry only. So now go to this area and look at the transport property. Okay, so we have a new beta, new is there. We required PR and PRT. This 2 entry is missing inside the transport property area. Okay, and this is no more needed. Okay, so let's delete that entry. Fine, so let's see. Then transport property can okay, so we required PR. Okay, say it is a PR, PRT. Fine, let's see. Cannot find a file. Which file? Turbulent property, sorry. So turbulent property file is missing, correct? So turbulent property, copy to our area, paste, and we want to run it for laminar, so type laminar only. Okay, so if it's a laminar, we need not to worry about k epsilon, all this thing. Now this Laplacian of alpha t is missing, so that is where it is missing, in the FV scheme. Okay, so go to the FV scheme area. So here Laplacian of that part is missing, and for that let's use the same scheme whatever we have here. Fine, so slowly we able to resolve. Then divergence phi of t is missing, that term, it's supposed to be here, and that term along with this entry. So we are set here. What else? Now t final is missing inside the FV solution. Okay, so FV solution we have a p final. Okay, we don't have a T final or that part. So let's go to this area, go to the system, FV solutions. Okay, we have a all is PCG. Okay, so let's check it. So it's smooth. So in case of the smooth, let's go with the BiCG type of the solver only, that is better solver. We find, and here PCG, it is, let it be GMG, and here we required one more entry as a T as well as one more entry as a T. Fine. What else we needed? We required this pimple base. Fine. We required the reference pressure and non-orthogonal character, everything. Let's say we keep it here. So let me check all this entry. Okay, so let's say in case of this we require all these entries and outer character, non-orthogonal character. Fine. Then that's it. I think we able to run the case. Let's see. So we able to solve the T equation, correct? Fine. So let's run with our new solver. Okay, incorporation of the energy equation in the Piezo algorithm. Okay, so ls paraform. So this is what we have, T. So look, temperature going to propagate with respect to the flow field. Okay, and here is the U and here is the temperature. Okay, so temperature, now we are solving as a proper energy equations. Okay, so that is what we are doing at present. So we incorporate the PR and the PRT. If we work with the turbulent flow, it goes with the PRT. Okay, it's PR, refresh it, let's see. So we run till 23, we have to run few more and we are set with the undulation. Okay, so this is how one can quickly adapt different class of equation inside the other solver and try to create our new own solver. So before it start shading, let's understand again. So what we did here, we adapted our pimple form, and inside the pimple form we want to incorporate the entire new equations, that is the energy equations. And so what we did, we went to the application area solver, and first incompressible pimple form we copied. Okay, and then we went to the heat transfer and Bossinus base pimple form. From there we add up the T equations and plug it inside our area, and then slowly we modified step by step, and then we come to know that our equation is okay. So step by step, when we adapted this all the terminology, we required certain changes inside the create field.h files. Okay, so appropriate change we did. Okay, so few entries required, we adapted. Read transport property.file needed to read the PR and PRT. Okay, so Prandtl number, laminar and turbulent Prandtl number that we needed. So all this change we made inside our solver, and then we create the test case based on the flow or circular cylinder, and now we able to run the case and we able to see that very nice vortex shading that is happening. Okay, so from the top and bottom vortex is detached. This is the temperature contour, I say. Okay, so let's run it from the scratch. So one can very quickly try to generate the different class of solver and try to add up the changes inside the OpenFOAM environment and create new solver and create new test cases and set up the entire environment inside the OpenFOAM, so that we can add up the scalar transport type of the equations. Okay, so I suggest you also try to incorporate these energy equations inside the Piezo form, okay, by your own way. Okay, and also generate this test case and start running this tutorial.